Hello and welcome to my spring 2024 research project, the hierarchical spectral clustering of timbre similar song segments. In this project, I created an algorithm that clusters song beats into segments using Ward's algorithm to minimize the variance of segments. This algorithm is made in order to automatically create tablato workouts to the timbre of songs. So the goal for this algorithm is to find approximately 2-to-1 length successive song segments below a given length threshold. So the algorithm consists of four main parts. We have beat feature extraction, Laplacian matrix creation, normalization of the Laplacian matrix, and the actual hierarchical clustering of the beats. So let's start with preprocessing. We start out by loading an audio signal using Librosa, and we calculate a log-powered constant Q transform from the signal. Then we synchronize the constant Q transform to line up with the beats of this in the song in order to reduce the dimensionality of the data. At this point, our CQT matrix is a size of number of beats times number of bins, where the bins are the constant Q transform bins, holding magnitudes of frequencies in these basically frequency bands. So we use this constant Q transform to create a recurrence matrix, which captures the timbral similarities between song beats. We also create a beat sync sequence matrix with a mel frequency capsule coefficient similarity between successive beats, and then create the similarity or sequence matrix from it. Both the recurrence and sequence matrices are combined into a balanced combination right here before we finally create a Laplacian matrix on that combination. The eigenvectors of the Laplacian matrix are run through a median filter and used to create a normalized Laplacian matrix. So this Laplacian matrix acts like a diffusion operator on the graph, modeling the spread of timbre throughout the song. At this point, we have a matrix of number of beats rows and number of beats columns, where the values at different positions indicate the similarity or connectivity between the row and column beats. However, we have a few problems with this. Using this matrix for clustering would cause us to basically cluster based on the noise in the data, since the scales of both of these CQT and MFCCC values are going to be bounded by noise in the data. And we want to reduce the effects of these outliers by z-score normalizing the data, min-max scaling it, and finally running PCA in order to scale the features uniformly. So PCA is used afterwards to reduce the dimensionality of data and make it easier to distinguish between beats. With this reduced matrix, we finally start clustering. The clustering algorithm is as follows. We start with a cluster for each beat and consider clustering each beat to the successive beat by minimizing the variance change of clusters, aka Ward's algorithm. We weight against larger and oversized clusters here before checking if every single cluster we are considering is oversized. If it is, we stop our algorithm and return these clusters. If not, we cluster the best nth percentile of clusters, which it's a given hyperparameter, and then repeat to the next iteration. This figure shows an example cluster history from the algorithm. The clusters formed in the first iteration of the algorithm are here at the bottom. We merge in multiple clusters in each iteration in order to speed up the algorithm. In later iterations, we start considering larger clusters since smaller clusters can no longer be made, and we are weighting this algorithm so then it'll try to cluster smaller clusters first so we don't get oversized clusters. At the top, you can see we eventually hit a point where we're no longer able to create more clusters after this one. And then we are given this result up here, which are the final clusters we found in the algorithm. You can see that they are an approximate 2-to-1 ratio, not perfectly, but this would correspond to a Tabata work segment, rest, work, rest, work, rest. Sometimes we have problems where maybe there's one beat and there's a ton of noise, like the beat was saved completely wrong. So that beat's gonna be like, oh, it's not like any other one, so it won't cluster. So talking about that, that's part of the future work. We need to make sure that we are weighting small clusters correctly, since these secondary segments, which are corresponding to rest periods in the song, are not always optimal. We need to improve the weighting of these clusters and better weight against larger clusters to prevent singleton clusters caused by audio noise. Additionally, The computational time of feature extraction is magnitudes above the clustering portion. This is the difference between 50 milliseconds at max for the clustering portion and in several seconds for the feature extraction. The feature extraction is using Librosa to load songs, and it's also using Librosa a lot to create these constant Q transforms, MFCC similarities. Then we're also using NumPy for SciPy and NumPy to create the Laplacian matrix. In the future, you probably don't really need a Laplacian matrix for this project. We could probably get by with just using the constant Q transform or just something that encodes the frequency or the magnitudes of frequencies in the song and then cluster based off that. We could scrap most of that and we can rewrite most of this feature extraction in NumPy. When I personally rewrote the old clustering to use NumPy, it provided a speed up of almost 10 times. It made a huge difference, and it'll probably make a huge difference if we use NumPy for the feature extraction. That's about all. I want to thank Dr. Patrick Donnelly for his help on this research project, being my project partner for my capstone.